Welcome. In today's video, we're going to derive the expected value and the variance of the Poisson distribution. To begin with, let us just remind ourselves of the probability mass function of the Poisson distribution. So, if x has a Poisson distribution with parameter lambda, then the probability mass function, or the PMF of x, is given by the following. We usually write P subscript capital X of x is equal to lambda to the x of e to the negative lambda all over x factorial, where x can take any value of 0, 1, 2, all the way to infinity. To derive the expected value of x, of course, it is a discrete random variable, we're going to use the definition of expectation for a discrete random variable, and that is given by the expected value of x is the sum across all x in the sample space of x of x multiplied by the probability mass function. We're now going to substitute in some values. So the support of x, or the sample space of x, is 0 to infinity. So that will be the terminals of our summation. X equals 0 to infinity. We've still got our value of x here, so that remains unchanged, multiplied by, and then we're going to substitute in our function above here, x factorial. Now, in the next step, what we're going to do is we'll do two things here. The first thing to point out is that at the very first terminal, where x is equal to 0, this expression here has a 0 multiplied out the front, and therefore it collapses to 0. So instead, we don't even need to start at x equals 0. We can just simply start at x is equal to 1 and go all the way to infinity still. Then we still write our expression times lambda to the x, e to the negative x, and I'm going to be a bit particular about the value of the x factorial, because as we know, x factorial can be written as x multiplied by x minus 1 factorial. And that's just going to allow us to cancel the x's in the next step. So let's do that in a more simplified manner. We've got x equals 1 to infinity of lambda to the x, e to the negative lambda on x minus 1 factorial. Now, the next step is perhaps not an intuitive one, but one that is common when trying to derive an expression for an expression for the expectation, particularly of discrete random variables. And what we're going to do is we're going to try and make this expression here look like an expression we're more familiar with. So for example, and by that what I mean is we're going to try and make it look like a PMF that we're familiar with. In particular, we're going to make it try and look like a Poisson PMF or another Poisson PMF. So I can see here, for example, that a Poisson PMF typically has an x factorial down the bottom, or in the denominator. Here we've got an x minus 1, which is a bit of a problem to deal with. So what I'm going to do what I'm going to do now is I'm going to strategically set a new variable, which is y, and I'm going to call that x minus 1. I'm going to label that or define that as x minus 1. And let's see what we get when we substitute in our values now. So in the summation, the first point to note is that when x is equal to 1, our y value, our new terminal, has to be equal to 0. and we still go to infinity because infinity minus 1, well, that's infinity. Our lambda to the x now can actually be rewritten as lambda to the y plus 1, and you get y plus 1, of course, because when you rearrange this equation on the side here, you get x is equal to y plus 1, and hence we've substituted in y plus 1 for x. Then our e to the negative lambda, well, that doesn't depend on any variables for now, so that just stays as e to the negative lambda. And then we finally have our y factorial down the front, or down the bottom, sorry. Now, what I'm going to again do, we're so close to looking like the PMF above, except with y's. The only difference is we've got an x up here, but we've got y's down here. We've got a plus 1. No issue. We can actually take the lambda to the 1 outside the summation because it doesn't depend, or it is independent of the terminal. So we can rewrite this as lambda times the summation of y equals 0 to infinity of lambda to the y e to the negative lambda on lambda factorial. And what do we know? This is now equal to lambda times the sum of y equals 0 to infinity of a probability mass function, we'll call it py of y, where y also is a Poisson random variable with parameter lambda. And we know by definition of a Poisson, or by definition of a PMF, when you sum the PMF and across the entire support of that PMF, then we get a value of simply 1. And so therefore we've got lambda times 1, and this simply becomes lambda. And that is how we derive the expectation. Let us now look at how we derive the variance. Now, of course, to derive the variance, the first thing we need to be able to compute is the expected value of the second moment of the distribution. Now, the second moment of the distribution is we're going to utilize this particular expression to find the expected moment of this, or the second moment, and I'll show it to you here. So we've got x minus 1 plus the expected value of x. This expression that I'm giving to you here, that is equal to the second moment, or the expected value of x squared. And I'm just going to prove that first to you, because if we expand the first term here, we get the expected value of x squared minus x, plus the expected value of x at the end doesn't change. Then by the properties of expectation, the expectation of a difference of random variables is equal to the respective expectations of the two variables subtracted from one another, plus expected to the value of x. And then finally, the final two terms, the minus e to e expected value of x plus expected value of x, cancel. And so we're left with an expression here, as I promised you, that this expression here is in fact equal to the second moment. Now, this is a very helpful expression. We've already derived the value for the expected value of x. What we don't have is a value for this component. You'll see why maybe we strategically use this expression, and it's similar to do with how we dealt with cancellation above up here. So let's explore a little bit why we've picked this particular variable, why we've picked this expression to use. So let's just focus on that first term. The expected value of x minus 1 is equal to, again, I'm going to use the definition of expectation. It is x across the whole support of x minus 1 times the probability mass function at x. We're going to substitute in our values or our terminals. Again, our terminals are from x equals 0 to infinity. We've still got our x minus 1, and now we're going to substitute in our PMF, lambda to the x, e to the negative lambda, all over x factorial. Now, similar to before, for the first terminal, when x equals 0, what does this expression go to? Well, you've got an x out the front, so you're going to have 0 times some expression. So it'll be 0. We can ignore it. When x is equal to 1, the next terminal, you've got 1 minus 1 in this expression. That becomes 0, and then you've got a whole expression that collapses to 0 as well. We can ignore it. So in fact, what we can do strategically is change the terminal straight from x equals 2 to infinity, and again rewrite our expression. Dot lambda to the x, e to the negative lambda, except I'm going to do a little strategic change here. Instead of writing x factorial, I'm going to write this as x minus 1, x minus 2 factorial. And again, by definition of what the factorial is, we can write that expression. And why have we done that now? Because now the x in the numerator, or the expression up there, cancels with this x, and this x minus 1 cancels with this x minus 1. And now you might be understanding why we use this particular expression for the variance. It is very useful when dealing with these types of PMFs because we can cancel this term typically with the denominator of the PMF. So now that we've done that, let's just tidy up our expression a little bit. We've got x equals 2 to the infinity of x to the lambda to the x, e to the negative lambda, all over lambda minus 2 factorial. And in a similar fashion, we're going to try and make this look like a new, or the PMF of a Poisson distribution. And by a similar token, what we're going to do is we're going to define y is equal to x minus 2 this time, or alternatively, x is equal to y plus 2. Both those could be defined here. What does this mean when we substitute or change our terminals? Well, when x is equal to 2, that means y is equal to 0. So we can rewrite that as y is equal to 0, and again infinity, because infinity minus 2 is still infinity. Now our lambda to the x becomes lambda to the y plus 2. Our e to the negative lambda doesn't change. And our x minus 2 factorial simply becomes y factorial. And in a similar vein to what we had before, we're almost at the stage where this looks like a PMF of a Poisson distribution. The only difference is that this lambda to the power of 2 here, we can actually again take that out the front of the summation because it doesn't depend on the index of the terminal. So we've got lambda to the y, e to the negative lambda, all over y factorial. And now again this expression here becomes the sum of a PMF. So for consistency, I'm just going to write that as lambda squared y equals 0 to infinity of a PMF where the PMF is, of course, a Poisson distribution with parameter lambda. And then, of course, we know that this simplifies to lambda squared as the sum across the whole support or sample space of a probability mass function is just 1 by definition. So we've derived an expression for expected value of x times x minus 1. This is going to allow us to derive an expression for the expected value of x squared, which again we defined before as this. Now we've derived the first component, we said that was lambda squared. We've derived the second part of this, we said that was simply lambda. And now finally we can compute the variance of the random variable. And the variance of the random variable is the expected value of x squared minus the expected value of x all squared, which in this particular instance is equal to lambda squared plus x minus lambda squared, which is just simply lambda. And if we want to complete this last part, the standard deviation by definition is the square root of the variance. And so we can rewrite that as the square root of lambda. And there you have it. We have now derived an expression for the mean, which was lambda, the variance, which was also lambda, and the standard deviation, which is the square root of lambda, for a Poisson random variable. I hope that derivation was useful. Hope to see you in the next video.